Hi, in this video I'm going to continue on industrial chemistry, and in this video I'm going to talk about first the chloro-alkali industry, and then I will talk about the methanol industry. So let's get started. Now, chloro-alkali industry basically involving the electrolytic reaction of seawater. Now, this is the overall equation. As you can see that sodium chloride reacts with water to form chlorine, hydrogen, and sodium hydroxide. Okay. Now, in this section, we will be talking about two actual electrolytic cells that are used or were used in the real industry. Okay. But before we step into the actual cell, I will actually want to refresh your memory about the electrolysis of solutions. Now, on the top right-hand corner of this page, I'm going to write down a setup that we often see when we talk about electrolysis in a core topic. Now, we have a beaker containing a solution, and there are power supply. Okay, and we have two inert electrodes, for example, platinum. Now, inside we have concentrated sodium chloride solution. Okay, sodium chloride solution, concentrated. Okay, let us just break it down, this electrolytic cell. Now, first of all, electrons come from the negative terminal of the power supply and gets down to this electrode. And this electron is waiting to be picked up. Now, as this electrode is attached to the negative terminal of the power supply, this electrode must be negative, and therefore this one must be positive. Okay? For the negative electrode, of course, it will attract the positive ions. So you will expect to see H plus as well as Na plus being attracted to the negative electrode. Now, who is going to be preferentially discharged and accepting that electron and undergoes a reduction? Well, of course, it has to be H plus. Okay, so on the negative electrode, you will expect to have H plus gaining electron, forming H2. Okay, and this is the reduction half equation. Okay. On the left-hand side here, at the positive electrode, somebody has to discharge so that electrons can be provided back to the external circuit and therefore balancing the charge. So here it is a positive electrode. Of course, it will attract negative species. In this case, we are looking at either hydroxide ion or chloride ion. Okay. Now, if you remember the electrochemical series, hydroxide ion is a stronger reducing agents than chloride ion. So based on the position on the ECS, we should have hydroxide ion undergoing oxidation on the positive electrode. However, here we are using a concentrated sodium chloride, which means the chloride concentration is much higher than hydroxide ion concentration. Therefore, due to concentration effect, chloride will be preferentially discharged in this case. Therefore, at the positive electrode, we will expect to have Cl minus forming Cl2 plus 2 electron. Okay? So, therefore, this is the two main half equation going on. And you can also see how hydrogen and chlorine are two of the three products. Okay? Now, what about sodium hydroxide? How do we form sodium hydroxide? Well, as the reaction proceeds, H plus and chloride are being consumed. What is left in the electrolyte? Well, of course, what we have left here will be a bunch of sodium ion and a bunch of hydroxide ion. Because these ions are not discharged, therefore they will remain in the solution. And these two ions will later on combine to form sodium hydroxide solution. Okay, so this is how we get the third product. Make sure you understand this electrolytic cell, because later on here, when we talk about the flow mercury cell, when we talk about the membrane cell, actually the reaction involved are the same as this electrolytic cell. The difference would be the design of the cell and some industrial consideration. Okay? So, if you understand this one, let's have a look at the two cells. First of all, we have the flow mercury cell. And this cell is said to be primitive cell. To be honest, nowadays we don't use this cell anymore. And we will explain why later. Now, in this case, pay attention to the electrode. So, in this case, the mercury is used as the cathode. So, the negative electrode is the cathode. Make sure you highlight this one. This is the negative electrode. Okay? And here, there is something interesting. Just now, we said that at the cathode, which is the negative electrode, H plus should be preferentially discharged to form H2. However, in this flow mercury cell, with the use of mercury as the cathode, it turns out that it is sodium that is preferentially reduced to form sodium metal here. Okay? So, down here, this is the first half equation. Sodium accepts the electron and then also reacts with mercury to form sodium amalgam. Okay? What do you mean by sodium amalgam? So going back to the top here, so actually sodium amalgam is an alloy. It's an alloy of sodium and mercury. Okay? So they actually forms an alloy. Okay? So this is something different than what we have predicted in the electrolytic cell. Okay, so this one you have to bear in mind. Now, what about anode? Now the anode is made by these electrodes. These are inert electrodes. Okay. Now, in this inert electrode, the half reaction is the same as what we have predicted. It is the chloride that is discharged to form chlorine. Okay. Now, so if you look at this diagram, when the brine is introduced into the reaction chamber, so there would be reduction of sodium ion into sodium taking place at the mercury electrode. Remember, mercury is a liquid, so this is actually a constant flowing stream of liquid from here down to here. You see there is a slope, okay? And you can tell at this inlet you should have mercury, but somewhere in the middle or towards the end you should expect to see some sodium amalgam that is formed. And this sodium amalgam will be removed from the reaction chamber. Okay? Now on this suspending electrode, these are the positive electrode, and these are the places where you will expect to see the chlorine being formed. So probably you will see some bubbles form on the surface of these positive electrodes. And after flowing through all these electrodes, the used brine, probably more diluted sodium chloride, will be removed. Probably we add the salt into it and then recycle it back to the brine inlet. Okay? Now, so from these two half equations, we have our one of the major products, the chlorine. But what about hydrogen and sodium hydroxide? So in fact, in this flowing mercury cell design, it actually has a separate cell. And this separate cell, the amalgam is allowed to react with water to form sodium hydroxide, hydrogen, and liberating the mercury. Okay? So this is how we get the other two major products. Okay? The mercury liberated will obviously pump back to the first cell, and it will again act as the cathode, and obviously it will be forming sodium amalgam again. Right? So this is how it works. Right? Make sure this equation is different from what we have expected. So this one you need to memorize it. Okay? So this is the first design of cell that you have to learn. Now on the right hand, so this one is more important. This is a membrane cell. So membrane cell is considered as a more advanced cell, and these days we will be using this membrane cell instead of the flowing mercury cell. Now, As a membrane cell, as the name implies, it has a selectively permeable membrane at the middle. And this membrane here allows sodium ion to diffuse, however, blocking other ions. So it only allows sodium ion to pass through, but not the other ions. Okay? Now let's look at this diagram and see how it works. Now we start from the top left-hand corner, where the brine is loaded into the chamber on the left. Now, the chamber on the left is where the positive electrode is stationed, and here at the positive electrode, you will expect to see the chloride ion discharged to form chlorine gas. Okay, so chloride ion here is attracted to the positive electrode, preferentially discharged it to form chlorine. Okay, and used brine will be carried away. Now, this chloride ion is unable to pass to the right-hand side because remember, we have a selectively permeable membrane, only allows the sodium to pass through. So on the left-hand side here, the chloride here will be used up. Okay? And when the chloride ion is used up, the sodium ion concentration increases. Okay? So sodium ion concentration increases. So when the sodium ion concentration on the left is higher than the right-hand side, there will be a net diffusion of sodium ion from the left to the right towards the negative anode. Okay? Now that works because the selectively permeable membrane allows the Na to pass through. So that would be the movement of sodium ion from left to right. Okay? Now, on the right-hand side here, you notice that we add water. Now, when water is loaded into the right chamber, and this is where the negative electrode is stationed, so here the H plus will be attracted to the negative electrode, and it will be discharged to form hydrogen gas, where we have the second major product. And then the hydroxide ion, as you know that, as H plus is being consumed, then the OH minus will increase. Okay. However, the increase in hydroxide ion will not result in the net diffusion from right to left because again, the membrane does not allow the hydroxide ion to pass through. So that means, as the reaction proceeds, you are expecting to see an increase in hydroxide ion concentration on the right hand side. Now, with the sodium ion on the left diffusing continuously to the right hand side, the sodium ion can combine with the hydroxide ion to form sodium hydroxide solution at a high purity, high concentration, and later on it is being pumped out and be collected, purified as the third major product. Okay, so this is how this membrane cell works. Okay. Now, just one more thing, pay attention to the nature of the electrode. Notice that the electrode used on the positive electrode is titanium, whereas the electrode used for the negative electrode is steel. Okay? There is a reason why titanium is used on this compartment. It is because here chlorine is being produced, and chlorine, part of it may dissolve into water to form an acidic solution. If you use steel as the electrode on the positive electrode here, then there is a chance where the iron in steel reacts with the chlorine, reacts with the acidic solution and get corroded quite rapidly. So therefore, titanium is chosen. On the other hand, on the right hand side, steel electrode is okay because on the right hand side we only have water. Okay, so there is no acidic gas being produced there. Plus the fact that if you remember in Form 4, we learned about factor affecting rusting. On the left hand side, the brine is actually a solution with large concentration of soluble salt. And with such a high concentration of soluble salt, it will speed up the rusting. On the right hand side, we only got water. Water does not have the dissolved salt, or at least much lower concentration. Therefore, the steel is less likely to be corroded or rust in this case. Okay? Even though it may rust in some time, but still can be replaced fairly easily and cheaply. Okay? So that is why such metals are chosen for the electrodes. Okay? Now the half equations are all predictable, not difficult. Okay. Now down here, something again important because we want to compare the two cells. You notice that both cells are designed such that different products are collected at different parts of the cell, are produced and therefore collected in different parts of the cells. Therefore, the products are not mixed together. Okay? And the advantage of it is to avoid any unwanted reaction between the products, and also you can add. Also, okay, it will make the product more pure or reduce the workup process in separation and purification. Okay? So you see how these cells incorporate designs which can facilitate the industrial process. Okay? Now, down here, this is also a very common question asking you why these days we only use membrane cell and we have already give up on the flowing mercury cell. So the reason why membrane cell is phasing out the flowing mercury cell is because no toxic chemicals are involved. Mercury is highly toxic. And secondly, it is cheaper to construct and operate the cell. I'm not sure about the construct, probably because the flow mercury cells has 2 cells, but here membrane cell only 1 cell. Now for operating the cell, you can understand that mercury is a very dense liquid, and you have to install pump to circulate the mercury liquid, which perhaps need quite a lot of energy to operate. And also, sodium hydroxide can be produced with much higher purity because of the membrane here, it blocks all the ions but the one we want, so that only sodium ion and hydroxide ion are able to meet each other on the right hand side and be collected with high purity. Okay, on the next page we have some practice question. You know the drill. Pause the video, attempt it yourself, resume the video, and check the answers. Now let's have a look. Electrolysis of concentrated sodium chloride is an important process. Write the chemical equation involved. So we have NaCl and H2O forming Cl2, H2, and then NaOH. You need 2 of these, 2 of these, and 2 of this. Okay? Down here, so explain the functions of mercury. So
it acts as of course, the negative electrode. So it acts as the cathode or negative electrode. Okay? It also alloys with sodium produced and transported to another cell for the production of sodium hydroxide.
okay. Now C, another cell is also used in chloro-alkali industry, which is called membrane cell. Explain the importance of membrane in the membrane cell. So first of all, you need to say that the membrane
is selectively permeable to sodium, but not other ions. Okay? So it allows only sodium ion to diffuse from the positive electrode to negative electrode, which then allows sodium hydroxide to form around the negative electrode with
high purity. Okay? Flowing mercury cells are gradually replaced by membrane cells. 2 reasons why mercury cells are being phased out, so you can copy back from the notes. You can say that, okay?
because toxic mercury is involved, but not in membrane cells. Okay? And also say that mercury cells are more expensive to construct and operate. Okay?
Okay, now let's look at the second question. Now we have a membrane cell. Okay, state the type of reaction that takes place at the anode and the charge of the anode. Very simple. So anode, bracket, and ox. So of course oxidation. And the charge of the anode. So the charge of the anode, you think about it, chlorine is being produced. That means chloride discharges. Chloride is negative, which is attracted to the positive anode. So it must be positively charged. So half equation takes place at both electrodes. So at the anode, just now I just mentioned 2 chloride becomes chlorine and 2 electrons. On the right hand side here, we have, of course, the H plus gaining electron to form H2. Okay? Explain how sodium hydroxide is formed with the aid of chemical equation. So we will say that
Sodium ion diffuse from the anode to cathode via the selectively permeable membrane and reacts with hydroxide ion to form sodium hydroxide. So Na plus reacts with hydroxide
to form sodium hydroxide. Okay? Okay? Good. Alright, so that's it for the chloro-alkali industry. Now, we will step into the methanol industry. Now, in methanol industry, we are talking about how methanol is produced from natural gas. And inside natural gas, we know that the major component is methane. So in other words, we are thinking about how we can convert methane into methanol. Okay? And there are 2 stages involved. First is called steam reforming, or we call it syngas production. Another part is called methanol synthesis. Okay? Now the first step here, steam reforming or syngas production. The feedstock will be methane and water vapor. Methane is coming from the fractional distillation of natural gases. Water vapor is very easy to get. Now, reaction, we have methane reacting with water vapor to form carbon monoxide and gas, hydrogen gas. The condition is given down here, nickel oxide as a catalyst, and we say that this product mixture, carbon monoxide and hydrogen, is called the syngas. Now, syngas, syn stands for synthesis. So this mixture of gas are able to synthesize something. Therefore, it is called syngas. Now down here, methanol synthesis is basically using the syngas to synthesize something. So we have the carbon monoxide and the hydrogen being the feedstock, which is coming from the syngas, which is coming from the steam reforming, right? So the reaction is simply the carbon monoxide reacting with hydrogen to form methanol, 1:2 ratio. Okay? Now the actual steps that is involved is having the formation of carbon dioxide first, and the carbon dioxide reacts with hydrogen to form methanol and water. Okay? And then these 2 can be cancelled out. But anyway, all we need to know is the overall equation here. Now the condition is milder as what we have here. So 300 degrees Celsius, 50 atm, copper and zinc oxide catalyst. Okay? Now, you notice that from the top here, the production of syngas will have carbon monoxide and hydrogen in 1:3 ratio. But down here, the actual requirement of hydrogen is lesser than what we have from the first stage. Okay, so you see, notice that not all hydrogen produced in steam reforming are used in methanol synthesis. Okay, so this methanol produced is separated by condensation and it is purified. So methanol can be easily separated by condensation because methanol has a much higher boiling point. with the hydroxyl group allowing it to form intermolecular hydrogen bond. So the product can be easily separated by condensation. Okay? So again, you have to memorize all these things. Now, on the right hand side here, we are talking about some alternative ways to produce methanol. Okay? Just now, methanol is produced from natural gases, and you know natural gases is a fossil fuel, meaning that the supply is limited. So we try to explore alternative methods to produce the methanol, perhaps from renewable resources. And one way of doing this is to get it from the biomass. So this process is called gasification of biomass. Basically, biomass are talking about the dead remains of organism, and inside we have a mixture of carbohydrates, lipids, proteins, etc. And within all these biomasses, they are rich in carbon and hydrogen. So the first step here, we have a step called gasification. Basically, we convert the huge biomass molecule into small inorganic gases. Okay? And from this mixture of gases, we introduce extra hydrogen, and we also remove carbon dioxide and methane, because the thing about it, by removing methane and carbon dioxide, what we have left is hydrogen and carbon monoxide, and guess what? It is the same as syngas, right? Similar to syngas. But of course, the hydrogen content may not be as much as what we want, what we need in syngas, because remember syngas has the ratio 1 to 3, or at least 1 to 2, right? So therefore we need extra hydrogen. We can get it from electrolysis of seawater, and we will have syngas in ratio of 1 to 2, which is able to be used in methanol synthesis. Okay? So basically, this gasification of biomass replaces the original steam reforming of natural gas by the gasification of biomass. And in both situations, at the end of the day, we will generate syngas, which is able to be used to make methanol. Okay? And the second alternative way is to make use of the fuel gas. And from the fuel gas, we have carbon dioxide, and electrolysis of seawater provide us with hydrogen gas, or this hydrogen gas may probably from the remaining hydrogen or from the steam reforming steps. Okay? Then anyway, we have carbon dioxide and hydrogen gas. They are able to react with each other to form methanol and water vapor. Okay? So this is another alternatives. Okay? Both methods can reduce the reliances or the demand of natural gases, which is pretty much limited. Okay? Now, down here, why do we have to make methanol? Well, because methanol is useful. Here, methanol can be used as the feedstock of making many organic compounds such as formaldehyde and acetic acid. Formaldehyde is the methanol, and acetic acid is basically ethanoic acid. Okay? Also, methanol can be used as a fuel for fuel cells in mobile phones and laptops. But this is very old application. Like nowadays, who will add fuels to their mobile phones or laptops? But in the past, we actually add fuels to the mobile phones and laptops. Okay? Okay, so that's it for the video.